Before we start this video, if you haven't prayed yet, pause the video and come back when you're done. Anyways, hello internet, I'm Dev Jr. ابن طارق ابن الفاروق ابن عمر ابن بنجس ابن موسى ابن يونس ابن تيمية ابن الصديق ابن Walid the first. And while studying physics for my current year of high school, I started looking into something called oscillatory motion. My professor explained this concept quite nicely, and I'm going to use his resources to show you how nice oscillatory motion is. Oscillatory motion is a part of a family called periodic motions. Periodic motion is a motion where the object returns to the main position every period, something like the motion of planets. The planets start moving, and then after a while, it returns to the same position, and we repeat the same motion. What happened here is a period. Now, in most periodic motions, the object returns to the starting/mean position only once per period. But in oscillatory motion, the thing oscillates across the mean position, having to go through it twice before repeating the motion. Oscillate is what we visualize as vibrate, like how a spring or a pendulum vibrates across a point. That point is the mean position. But how does that even work? I'm going to visualize the physics using a Unity simulation I made, but in short, there are about 4 main forces in all types of oscillatory motion. First of all, the restoring force. When we stretch something like a spring or hang a pendulum, there is potential energy here because the spring/pendulum are not in their position of lowest energy. So this potential energy will turn into something called the restoring force. In a spring, because we're basically just squeezing the particles or stretching them, they want to be together but not two together. So they will start to pull each other together or push themselves apart, giving us the restoring force. The restoring force always points to the equilibrium position. The equilibrium position is where the net force is 0, and the particles are now in their optimal state. The restoring force equals negative the displacement from the equilibrium position times something called the spring constant. Now, this spring constant is determined by a lot of things: the type of material, the elasticity, the temperature, the diameter of the spring wire, the diameter of the coil, the number of the turns, the length of the string, etc. I'll go over one that got my interest: elasticity. The elasticity, which is determined by something called Young modulus constant. The thing itself is pretty complex for this video, but one fun fact about it is that iron is more elastic than rubber. Because elasticity means the ability to handle a lot of force and deformation, and then being able to go back to the undeformed state. And that in iron is much stronger than in rubber. Now back to the restoring force. If I just ran the simulation with only the restoring force, you would see that when the object is already stretched, the restoring force would be at its highest. Then it will start accelerating the object into the mean position. When the object reaches the mean position, the displacement is 0, so the restoring force is 0. Equilibrium. So the particles should stop now since they are in their equilibrium position, right? Wrong. The acceleration may be 0, but the velocity is still untouched. Actually, it will be at its highest, and the particle will zoom across the main position. But now, the particles have gone back to that uncomfortable state, so they will start to create a restoring force again, but in the opposite direction, causing the velocity to decrease and decrease until it reverses, and the body reaches back the equilibrium position. And then we repeat the motion. That was one period taking one periodic time, or t. If we regraph this displacement and the velocity, we would see that when the displacement at its lowest, the velocity is at its highest, and vice versa. But do you notice another thing too? The graphs here are similar to a sine/cosine function. Now, let's explain the law. Displacement equals the amplitude times the sine of the angular velocity times the time. Now, what is all that? This graph is a displacement over time graph. The amplitude is the maximum displacement. Let's say that we let the spring go from a position of 3. If we're working with no other forces but the restoring force, then the amplitude will stay 3. The sine function gives us that periodic trend we're seeing. And now, what is the angular velocity? Now, the thing about cosine and sine functions is that they take an angle and return values from -1 to 1. Now, time is not an angle, so the angular velocity is 360 degrees over the periodic time. So basically, after doing all the math, the angular velocity's job is giving the sine function an angle that represents the elapsed time of the simulation, giving us this trend. And now we want to graph the velocity. And as we know, velocity is the rate of change for distance. So one thing that we took in math that represents rates of changes are derivatives. And before we close the video, don't worry, I'm not going to explain differentiation or derivatives, but basically, to get the velocity law, we'll basically get the derivative of the displacement function. And poof, we don't have to check the math, don't worry, stay in the video. So as you can see, when we run the simulation now, we'll get a graph that is a cosine function. But the thing about a cosine function is that it's shifted back by 90 degrees, which gives us the relation we were talking about: lowest displacement, highest velocity, and vice versa. Now, one thing about a spring and an empty void with no air resistance is that its energy is constant. How? Because we have the law of conservation of energy that tells us that energy, or the net energy, is equal to the potential energy plus the kinetic energy. And we know that the kinetic energy is equals to half the mass times the velocity squared, which is proportional to the velocity. And the potential energy is equal to half the spring constant times the displacement squared, which is proportional with the displacement. So because of the sine-cosine relationship between velocity and displacement, both will keep adding up, causing a constant net energy. But you might say, but Dev Jr. did type the first. If I got a spring and let it go, it will stop after a few seconds. Great observation. That's because of our second force, which is... Now imagine instead of the medium of the spring being an empty void, we fill it with a bunch of air particles. And as you can see, the spring now has to push these particles out of its way. To push them, the spring has to transfer some of its energy to the particles. And as more and more energy gets transferred, the spring starts to lose its energy. And when the kinetic energy decreases, the velocity decreases too. So the distance that the spring travels over time shortens, and it continues shortening and shortening and shortening until the body stays still. What was happening here is what we call damping. Now, in the simulation, we don't have to do any complex energy transfer equations to achieve a result. So there is a force called the damping force. It equals negative the velocity times the damping constant. The negative here shows us that the force acts opposite to the velocity, slowing the spring down. The damping constant here is determined by the medium where we're working in. There is no set clear value, so I'll just set it to 1. But fun fact about it is that it is proportional with the density. So the denser the medium we're working with, the higher the damping constant, and the faster our oscillatory motion would go back to 0. And as you can see, when we redo that simulation with the damping constant of 1, the body will slowly lose energy and go back to a still state. Now, the law showing that relationship has some new stuff. I'll not tackle the angular damped velocity, but here is the law if you're curious. The thing I want to tackle here is the damped amplitude. It equals the maximum amplitude times the Euler's constant times negative the damping constant over double the mass times the elapsed time. So this expression over here represents something called an exponential decay function, which basically means that over time, the amplitude will decrease and with it, the displacement, giving us this graph at the end. Now, we have been pre-hanging the thing every time we want to simulate. Can't we just grab it and do that in real time? Now, to do that, we will go back to our third force, which is... The applied force isn't really that complex. We'll just apply an amount of force using my arrow keys to the net force. And voila, we have an applied force. Now, that looks simple, but it has some pretty cool results. First of all, if I'm continuously adding force, shouldn't this thing be pulled forever until it breaks? Well, yes, but no. Because the force affecting the velocity is the net force, and the net force has to be more than 0 to make a change. And I'm applying a constant force to the net force. It will reach a point where the restoring force is equal to it, causing the net force to be 0. Another interesting thing is that if I start applying my force periodically, a pattern will be formed. Because we have the restoring force and the applied force, now both periodic, the graph show wave-like behavior. And one thing about waves is that they interfere and combine. That combination is the net force. Now, there are two types of interference that cause our combination: destructive interference and constructive interference. Destructive interference is when the crest of a wave meets the trough of another wave, canceling each other or producing a weaker wave. This happens when the waves are 180 degrees apart. This phase shift causes the pattern that results in a destructive interference. Now, constructive interference is when the crests meet, when the waves are in sync, creating a stronger wave in the same frequency. And as we learned, that stronger wave will lead to more energy and in return, more amplitude. So, in the law for forced oscillatory motion, you would see that the amplitude determined by subtracting the angular frequency of the forced motion and the natural frequency of the spring. It's only when they are equal that we get the lowest denominator. And a low denominator means a high resultant, aka a higher amplitude. This is called a resonance. In oscillatory motion, a resonance is where two frequencies match, causing a much higher amplitude. This is actually how earthquakes happen. Let's say the ground's particles have a certain frequency in which they oscillate, and a seismic waves comes with the same frequency, causing a resonance. The higher amplitude will mean the particles will start oscillate so much that they break apart, causing the cracks after an earthquake. The last force is gravity, but it's really nothing new. Imagine a constant applied force pushing downwards. Yeah, that's it. Anyways, that was my video PSA on oscillatory motion and springs. Don't forget to pray, and I hope you have an amazing day. Bye.